Okay, so today I want to talk about the Klein Gordon equations, Lagrangian. So we've gone over Lagrangians a little bit. Basically, what we want to do is we have our Lagrangian, and I'll introduce a little bit of nomenclature here. But this is our Lagrangian that we see for, or that we have for our Klein Gordon equation. Now, you might think this comes out of the blue, but it won't, okay? Here we have our, I'll zoom in a little bit. Here we have our, at the sort of the adjoint to our solution. So this here's the solution, and this here is something of the complex conjugate of the solution. And we're going to see when we apply a certain set of rules to this, right, specifically the Euler-Lagrange equations to this, then we're going to recover these guys right here, right? These are essentially the same thing, right? The only difference is that there's these guys right here. This is the adjoint again, or the complex conjugate, and this is the solution. So this is complex conjugate to the solution. And these should work for the solution and its complex conjugate. And so, yeah, so again, these guys right here, Klein Gordon, this is Klein Gordon also. This here is called the D'Alembert operator. This is a combination of the spatial derivatives and the time derivative, okay? Now, we've derived this before. And I'm not going to derive it again, but you can go back and you could take a look at the video that did derive the Klein Gordon equation, and you can take a look at the similarities between this here and this here. The only difference, again, is that the Klein Gordon equation should work on the complex conjugate of the solution. Right. So I can't remember actually if we've actually gone over the Lagrangians. It's been a while, but essentially what Lagrangian is, it's sort of this canonical equation that when you apply the Euler-Lagrange equations to it, you get back your differential equations. So you can sort of think of the Lagrangian as this thing that it's a function of functions, right? These guys are functions. This is a function, that's a function, it's a function of functions. And it's a function specifically of the derivative of each solution and its position, right? Okay. Now there's a reason I have this alpha and this mu here, but I'll get into that later. And then these guys right here. I didn't go over these. This is sort of an added, sometimes you won't see these in here. Depending on where you read, an upper index means, I believe if I remember correctly, an upper index means that this is a free particle, right? There's no real outside influences defining any potential, right? So the potential is not there, and this is a spin zero particle, right? So you could have 0, 1/2. So this is something like this. And in that case, that would be the Dirac equation. And we haven't gotten into the Dirac equation yet, but we will. Dirac equation's real fun. Okay, so let's start applying the Euler-Lagrange equations. So here they are in, I actually didn't write out the Euler-Lagrange equations explicitly, but what we're going to want to do is we're going to apply these Euler-Lagrange equations to our Lagrangian, and we want to see if we get these guys back, and we're going to do that right now. Okay, so let's start off with this right here. So this guy right here explicitly is supposed to equal this guy. That's what the Euler-Lagrange equations tell us, that the derivative of the Lagrangian with respect to the change in the variable is equal to the negative of this guy, right? So and we can derive that. That comes from that comes from a principle of least action, which I haven't really gone over yet, but I'm going to assume some things are known within the audience here as we go into quantum field theory, because I can't really start from scratch with quantum field theory. I have to assume some things about you guys and about the nature of the people who are watching this. If you do want a derivation of the Euler-Lagrange equations, simply put a chat at the bottom of this video, or you can I'm sure you can find a derivation of the Euler-Lagrange equation somewhere else on YouTube somewhere. But if you explicitly want me to do one, then I will go ahead and do it. Just send a chat in the video and we'll be all good from there. So what is the derivative of the Lagrangian with respect to the change in the coordinates? Right. This isn't a double derivative, right? Because there's no 2 right here. But what this is literally saying is that we can kind of rewrite this as like Lagrangian over, here I'll write it with an actual pen, the derivative, oh, my thickness is 2, the derivative in the Lagrangian with respect to phi dot is sometimes how you see this, and phi dot is a derivative, right? So it's these two things are somewhat synonymous with one another, okay? And so let's see here. So we're going to take this derivative, this is this right here, and we're going to put in our Lagrangian. Now the reason this isn't in here is because, well, what happens if we take the derivative with respect to derivatives? Well, there is no d mu in this component here, so that's 0. That's why it's not in here, right? So if this was d mu like this, then the derivative, then there would be something for this, but there isn't. There is no d mu. There is no d mu right here. So that's this part right here. This part right here is this part right here. Okay. This is a Minkowski metric. This is this can just get this raises and lower indices. This can be brought out here, so I'm doing that right here. Okay. Now we have the derivative of this. Okay. Well, this is chain rule, right? So we want to apply this to this, and apply it to this. So let's apply it to this first. When we apply it to here, we get this guy right here. And this guy gets tagged along because that's chain rule, as we all know from calculus. Again, I have to assume that my audience knows calculus here, which is a big assumption to make, but if you're interested in quantum field theory, then I'm inclined to think it's not that big of an assumption to make. All right, so, okay, so now we have this guy, which is right here, and we do derivative on this guy. All right, so we do here, and then we do here, and we have to multiply by their, by the things that are not taking the derivative of. We're not taking the derivative of. Right. So this is chain rule right here. Now what? So now we realize something interesting, right? So the derivative of this with respect to this, well, these two things are the same, right? So that's going to be 1. So we're just left with this. Right, so that's right here. The derivative of this with respect to, well, that would be 1 if mu and b were equal, right? So we put this right here. If mu and b are equal, we use this Kronecker delta right here to say that, okay? So now we have this right here. Minkowski metric stays out here. Right, so if mu and b were equal, we would have this right here would be the same as this right here, because we're contracting over indices. So we get 2 of them. So that's where this 2 comes from. Okay. we're getting close here. Right, so we have now that this, which is from up here, this guy right here, is equal to this, which is what we came to right here. Okay. So now we can we have this beta and we have this beta. Right, so now we have alpha. Right, so that's raising lower indices. I haven't really done anything on tensor calculus yet. This isn't really a tensor calculus thing, but to me it is. And I will create a separate playlist on tensor calculus, in which you can follow along just like I'm doing here. Okay? That's not, the tensor calculus playlist isn't here yet. So what do we have? So we have, let's see here. So we could just take a derivative, the alpha derivative right here. We're not doing much. We're just placing another derivative right here. Now, the reason we're doing that is because this right here is part of the Euler-Lagrange equations. We're going to say that this right here is equal to this. Okay? Okay, so let's take a look at this guy. The derivative of this with respect to phi, we're going to get that from up here, from this guy right here. Right, and so what we're going to get is that that's this right here, okay? So that would be this guy right here. Okay, so what is the derivative of that? Well, that's just bring this over like that. This calculus, right? So we get this. And the reason we don't have this right here is because this would be for these two theoretically should be the same if we're dealing with a real scalar field, right? If it's complex, then it's going to be different. But we're doing a real scalar field for right now. Okay. So now we set this guy equal to this guy. So that guy equal to that guy, and what do we get? Well, here's what we got for this guy right here, and here's what we have for this guy right here. 2's can cancel out, right? Now, lo and behold, we have this plus this, right? We just move this guy to the side, and we change that minus, and voila, we have our Klein Gordon equation. So that means that this right here is a valid Lagrangian to represent the dynamics of our Klein Gordon equation, which is right here. Okay? So that is the Klein Gordon Lagrangian. Keep in mind that I have talked about Lagrangians in the past and what they represent, what they mean. Again, a Lagrangian is a function of functions, right? We're going to figure out what the Lagrangian for the Dirac equation is, but these Lagrangians essentially are mathematical things that take us from that sort of when we act on them with the Euler-Lagrange equations will give us our differential equations that we want. And the differential equations that we'll be primarily interested on are the Klein Gordon equation and the Dirac equation. And then there's going to be the Proca, which I've mentioned before. There's an A at the end of that, Proca, which I've mentioned before, but we'll get into that one later. That has to do with electromagnetism. So I'll see you guys in the next one.